In the last class, we discussed about the basic Feistel structure, which was first introduced, and then we discussed about some improvement which was done because of the disadvantages of that initial Feistel structure, right? And I also told you about these elements which we use in a Feistel structure, which are these block size, key size, number of rounds, sub-key generation, and sub-key generation algorithm and round function. Okay, so these elements we use in each and every Feistel structure. This block size tells you that the block with which you are dealing with uh, at a given time, it tells you about the size of that block. Okay, and I told you that this size could be 64 bits, it could be 128 bits or 256 bits and so on, right? This key size, again we have to change its value for each and every round. Then the number of rounds, it uh, it it shows that how many rounds do we have for a given Feistel structure, right? Then the sub-key generation algorithm, this algorithm, on the basis of this algorithm we generate the key for each and every round. Then the round function is the function which we the if you remember the component which we used in previous class, in which we perform an operation or a series of operation to find out the value of the Cipher text, right? So on the basis of that function and the given key, we find out the Cipher text. Okay, so these are basic design elements of any given Feistel structure. So today we'll be discussing the final Feistel structure, which many of the algorithms use nowadays. So the problem which we had with the previous structure, which was the improved structure, the problem we had was the right part of the plain text. So the disadvantage the improved physical structure had was that the right half of the plain text, it never changed, right? So the attacker can immediately find the right half of the plain text by intercepting the cipher text and extracting the right half of it. So the design needed some more improvement. So in this design, we have increased the number of rounds, and then we added a new element which we call as swapper. Okay, so here it is. This is swapper. This is the new element we have in this final design, along with this mixer which we had in previous designs as well. So these two new things which are increasing the number of rounds and including this swapper into the design of Feistel structure. So the structure was modified with these two new elements, right? So the swapper which we use over here in the encryption, this swapper and this swapper, the effect of these swappers will be reversed by the swappers which we use at the decrypting end. Okay, so the swapping which is done over here at the encrypting end will be reversed at the decrypting end using these swappers, right? So how this whole final design of Feistel structure work? Most of the things are same, but this inclusion of swapper, it involves the right part of the plain text in the in the whole process as well, which was not included in the intermediate structure, okay, which we discussed yesterday, right? We called it improved Feistel structure, right? So we have discussed two structures before, and this is the third one structure, which is the final design. So in this, what we are doing is we have again partitioned the plain text into two parts, which is the left part and right part. We have denoted it as L1 and R1. Okay, then we have used a mixer and then a swapper. So now how this R1 is included into the process. Now we can see it from here that this L1 goes to this XOR operator, okay, and this R1 goes to the function, and this function is performed using R1 and this key K1. Here this key is K1. This is the key for first round. Right. So this is it belongs to first round. So we have named it as K1. For the second round, we'll have this key K2. Now this function f, it is being carried out using this value of R1 and K1, right? And this output of this function component and this L part, which is the left part of the plain text, they are XORed over here, right? So after XORing it and this right part of the message, so both of these values are swapped using swapper. In the previous design, what we were doing, we were simply using this right part of the plain text as it is in the next level, right? Or in that previous design we were not having a number of rounds, तो उसमें हमें final cipher text ही हमारा ये मिल रहा था यहाँ पे, right? So there was no middle text in that example. But here we are having two rounds. Okay, this is an example of two rounds, and we are using a swapper also. So what does this swapper do? It swaps the right and left part of the message, right? तो यहाँ पे जो calculation हुई XOR operation करने के बाद, so this is the left part and this is the right part of the message. So left part has been made the right part of the message, and the right part has been made the left part of the message, right? So this is the task of swapper. Now here at this stage, now we are having this middle text with us. Okay, middle text, I told you these are the intermediate text when we use multiple rounds for this given structure, right? So now this L2 and R2, they will act as input to the second round, which is over here. Okay, again we'll be having all these components, this mixer, this swapper, this function, and all these things, right? The process will be same. L2 and the output of function using R2 and K2. Okay, because these are the input to this particular round. So the output of this function and L2, which is the left part of the middle text, they will be XORed and it will be swapped using the swapper. So this left part of the middle text will be made the right part of the text, and this right part will be made the left part of it. Okay, so now we have the encrypted message with us. Because this structure has only two rounds, we can have more rounds as well. But here we are showing this this example having two rounds only. So now we have this Cipher text with us, right? So this is L3 and R3. So these are left and right parts of the Cipher text now. Now after transmitting it over the channel, we have represented it using L4 and R4. Okay, so this L4 is equivalent to L3 and R4 is equivalent to R3. Now at the decrypting end, we will again use swapper and then mixer, but the order of their use will be reversed. So first we will use swapper and then we will use mixer. Okay, here at the encrypting end we first use mixer and then swapper. So here that order will be reversed, जैसे हमने previous जितनी भी ciphering techniques करी हैं उनमें किया है, वैसे ही हम सारी चीज़ों को रिवर्स ऑर्डर में यूज़ करेंगे. So what we are doing is we are making this left part of the cipher text as right part and the right part as the left part. Right. Now at this mixing stage, what will happen? We'll use this K2, okay, and this L4, which has now become the right part of the cipher text. We'll use this L4 as the input to the function component along with this key K2. So the output of this function and this right part over here will be XORed, okay, and the output we get, we will in the output we will get the left part of the middle text, right? And this after swapping or after making this left part as right part, it will directly go to the right portion of the middle text. So here at this particular stage we have got the left part and the right part of the middle text. Now again, since it is having two rounds, so for the next round and next and final round, we will again swap these parts of the middle text. This R5 becomes the left part of the middle text, and this left part becomes the right part of the middle text. Now again the same process will be carried out. Here this is not R5, this is L5. Okay, so just read it as L5. This is L5 and the key we are using at this particular round is K1, right? So the output of this function and this R5, this value of R5, which has become now L5. So we will be using it as the input, right? So here you can yes, you can write it as R5 R5 as well, because ultimately we are making use of this uh, no, I'm sorry, so this will be L5 only, right? Yes, this will be L5 only. Okay, so here this will be the output after XORing these entries, right, which is R5 and the output of this function component. Fine, so we will get this left part of the message and this right part will get after swapping it from here, right? So this is how we get this plain text back. Now we have to confirm that whether this L1 and L6 are equivalent or not, and R1 and R6 are equivalent or not. In that intermediate version of Feistel structure, which we discussed yesterday, this right part of the plain text was not changed, right? So there we were taking it as it is, so we did not perform any calculations, or we did not check that whether these right parts are same or equivalent or not. But here we are swapping the left and right parts of the message, so we have to check for the right part of the message as well, whether they are equivalent or not. So you have to confirm that this L1 is equivalent to L6 or not, and R1 is equivalent to R6 or not. But before that we need to confirm that these parts of the message, which is the middle text, they also must be equivalent or similar. Okay, because if they are not similar, then there will be a problem at this particular round. Fine, so I'll show you some expression which we can use to check whether these left and right parts of the message are equivalent or not, right? So the expressions are just like the expressions which we discussed yesterday while discussing about that improved Feistel structure, जो second level है Feistel structure का. So I'll show you the expressions. So here are these expressions with which we can prove that the plain text which we have encrypted, we get the same plain text after decrypting it. Okay. So if we see that if L6 and L1 and R6 and R1, if they are equal, then we say that this plain text and this plain text which we are getting after decrypting it, they are same. Okay, and we assume that L4 is equal to L3 and R4 is equal to R3. So that is the thing which I told you earlier as well कि यहाँ से जब ये channel के through message जाएगा यहाँ पे, so we assume that this left part of this encrypted message and the message which we have over here, they are same. So L3 is equal to L4 and R3 is equal to R4, right? So first of all, we'll be proving the equality of middle text. Now middle text involves L2, R2 and L5 and R5, right? So it says, say now R5, we can see it from here. Now you can see that R5 is equal to what? It is equal to L4, right? L4 is equal to L3 and L3 is equal to R2, right? So from these connections we can prove that R2 is equal to R5, right? R5 is equal to L4, L4 is equal to L3 and L3 is equal to R2, right? So the right part has been proved that it is same or similar. Now we have to prove for the left part. So what we'll do is we'll start with L5. Now this L5 is made up of this expression. Now we can see it from here that this L5 is made up of the XOR operation between what? Between R4 and F L4 K2, right? So that is the same thing written over here, right? R4 XORed with F L4 K2. Now we can change this R4 with R3. Now we have to prove this relation between L5 and L2. So we have to convert this expression into a form which consists of L2. Now this R4 is equivalent to R3. From here we can see, right? So we have changed it to R3. And this L4 is equivalent to R2. We can check it from here. This L4 and R2, they are equal. So this expression is changed to this expression, right? Now here we can check that the value of R3 over here, okay, because we have to convert this expression into some expression which consists of L2, because we have to find out the relation between L5 and L2. Now R3 we can check it from here. This R3, how are we finding it? We can find it out using L2 being XORed with FR2 K2. Okay, L2 XOR FR2 K2. So this is the same thing which we have written over here, L2 XOR FR2 K2, right? And this expression is same as it is over here. So we have replaced this R3 with this expression, right? Next is we, I told you in previous class as well that the same value when you XOR them, then the result is 0. So the both of these values will be discarded and we are left with L2. Fine. So this expression is equal to L2. So it proves that L5 is equivalent to L2. Right. So we have proved the equality of middle text. Now this middle text is equivalent, right? And now we have to prove the equality of this L6 and L1 and R6 and R1, right? So how we can prove it? Say right part अगर हम पहले लेके चलें तो R6 is equal to L5, which is equal to L2, and which is equal to R1. So we can see it from here. This R6, this is equal to L5, right? This L5 is equal to L2. We have already proved it. So L5 is equal to L2, and L2 is equal to what? This is equal to R1, right? So R1 and R6 are proved equal. Now we have to check for L6 and L1. So we'll use the same expressions जैसे हमने L6, how we have obtained L6, and then how do we obtain R1. So we'll use the same method which we have used over here, right? So I'll just brief it shortly. So L6 we are getting using this expression, right? So this is L6, which is R5 XORed with F. Now this is L5 over here, okay? L5 and K1. So this is R5 XORed with L5 and K1. We can now replace this R5 with R2, okay, from this expression, because R5 and R2 are same, are equivalent. And this L5 is equivalent to L2. So we can write L2 over here. Then we can find out that how do we calculate R2. We can check it from here. This R2 we are getting using L1, okay, this L1, and L1 XORed with FR1 K1, right? So this is the same thing written over here. So this R2 has been replaced with this expression, and this L2 is equivalent to R1 from these equalities, okay? So L2 we have replaced with R1. So again these two entries will be discarded and we are left with L1. So hence it is proved that L6 is equivalent to L1, right? So that means the message which we are encrypting over here, which goes through multiple rounds and multiple components, when we decrypt that message, we are getting the same plain text over here, right? So this is about Feistel structure, and this is how it works, using multiple rounds, using multiple components in a single round, using a different key for different rounds. Fine. So this is all about Feistel structure. Now we will be using this structure for understanding the upcoming ciphering technique algorithm, which we call as DES, okay, data encryption standard. After this we have this non-Feistel cipher. Non-Feistel cipher जो मैंने आपको previously भी बताया था, that this cipher uses only invertible components. Feistel के अंदर we can use self-invertible, invertible and non-invertible components, but the structure which uses only invertible components, those structures are called non-Feistel structures. Okay, so that is all about this Feistel structure or Feistel ciphering technique. Feistel cipher also we call it. So that's all about it.